our first thing is to understand the logic why we need to break tensors into components. You remember when you were introduced to vectors in secondary school, and they now had to break it into IJK. If you remember correctly, you were happier working with IJK than working with the original vectors themselves. It's easier. So when there is a decomposition of a vector into the coordinate components, you can always find the coordinate components, you know how to find them, and you know that it is everything, even cross product, dot product, whatever you want to do with the vectors, they are easier to work from the component. It's the same thing with tensors, with a slight difference. We can break vectors into their components only in one way. Tensors can be usefully broken down in several different ways, and many of them are useful. There are at least 9 ways you can decompose tensors, and that are very, very useful. So even though for vectors, you can only do that in one way, IJK, or E1, E2, E3. For tensors, it is different. Some of these decompositions, like the component form, are additive. Some of them are additive. Some of them are multiplicative. That is, it is multiplicative. You can break a tensor into 2 components, and the original tensor is the product of the components rather than just the addition of the components. When it is like that, you say that the decomposition is multiplicative. So just know that, do not get confused, do not get distracted. Just know that we are just introducing several different methods of breaking that. Every one of them is easy, eventually easy, if you know what you are doing. But if you just want to carry all of them in your mind at once, it looks so hairy and difficult. And maybe somebody has told you that, that thing is hard. There's nothing hard about it. Just know that what we are trying to do is that we know that sometimes it is easier working with decomposed vectors than working with the tensors on their own. For instance, you remember in the top right corner here, if you have a vector f, you say it is fi, f1i, f2j, f3k. You are familiar with this type of decomposition. And we don't use ij and k any longer like this. We use e1, e2, e3. That's what we use for instead of, but it's still the same thing. And you know why we are doing that. It is easier for us. Not only so, there's another way you can look at it. You can see that every vector is ijk. It's just what weights you should put on I, j, and k. You call those weights components. So you can see it as a weighted decomposition. You just break them into weights, and you call those weights components. That's all that you are doing in your vector analysis. So component form is weighted sum of dyads. There are 9 dyads: E1, E2, so E1, 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 E2, E1, E3, all the way until you get to E3, E3. And we saw last week that even when they look alike, they are not related at all in any way. So E1 dyad E2 is not the same thing as E2 dyad E1. They are different. So there are 9 bases for the tensor, whereas you have only 3 bases for your vector. So that is, once you remember that, there's nothing you are doing differently from when you were dealing with your vector analysis. There's nothing really fundamentally different. So there are, so in component form, you are breaking them into 9 bases. Now, we have talked about the component form. There are 3 other additive decompositions apart from the component form we looked at. We can break a tensor into skew and symmetric and skew parts. That is another additive decomposition. We can also break a tensor into spherical and deviatoric parts. That's another additive decomposition. We can break a tensor into a spectral form called eigenbasis. That is still a 3rd method. Each one has its own very, very important use. Now, then there is the multiplicative decomposition, rotation and stretches in polar decomposition. In fact, this is what is most important for engineering, because when you have a body that is stressed, you can break that stress into two tensors. One is a rotation tensor, the other one is a stretch tensor. It is when you multiply those two together, you get the final thing. And it is easier to deal with the rotation and stretch separately than to deal with the original tensor. The tensor in this particular case is called the deformation gradient. It's a very terrible tensor to deal with. But if you break it, but every deformation gradient can be broken into rotation and stretches. When you break them into rotations and stretches, they are much easier to deal with, and that is a multiplicative decomposition. We are now going to go through these ones one by one slowly. We are not going to move too fast. So, but before we do that, this was where I stopped teaching last week. That the trace of a dyad, which is also the first principal invariant of a dyad, that the trace of a dyad is the same thing as the dot product of the two elements of the dyad. This is the proof. So if you want the trace of the dyad, this is the formula for any tensor you want the trace. You put the tensor here, E2, E3. You put the tensor here, E1, E3. And you put the tensor here, E1, E2. Remember that these square brackets represent vector triple products. Scalar triple product. They represent scalar triple product. From this line to this next line is very easy, because you know that if you open this dyad, what you have in the first bracket is V dot E1. That is the first component of V. That's the component of V in E1. That's why you have that V1, and then in the direction of U. That's what you have here. We do it in the second case. You see it is V2 in the direction of U, and then the third one is V3 in the direction of U. And then E1, E2, E3. This triple product of the three component vectors that are orthonormal always gives you 1. Like I dot j cross k is 1. I cross j dot so this E1, E2, E3 will always give you 1. So that is the thing, because you do so when you do the dot product, the cross product first before you do the dot product. Otherwise you get 0. So this is a triple product. If you don't remember your triple product, go to the first chapter where we are dealing with vectors. You'll see it there. Now, so what you now see in this bracket is V1U dot the cross product of E2, E3. And then this again is V2U dot the cross product of E3, E1. And then this is V3U times the cross product of E1. This one will now be okay. There's an error here. This is E1, E2. There's an error in this place. This is E1, E2. Yeah. Not E2, E3. And we got it right in the next line. So when you have that, when you have this line here, you now will see that this is, if you open this one, you have 231 E1, 232 E2, 233 E3. You see that 2 of them will vanish. The only one that will survive is 231 E1. Similarly, this one will be 312 E2. That's the only one that will survive. This one will be 123 E3. All the other things will fail. If you will become 0. If you now add this up, you are going to see that this is E231. This is 1. So you now have U dot E1. So that is U1. E2 dot U2, this is U2. You will see that E231, E312, and E123, all of them are 111. So you now have that. It is when you do the trace of U circle times V, what you just get is U. What you just get is U dot V. That's all. So that is it. So anytime you try to take the trace of a dyad, just take the dyad symbol away and turn it to dot. Finish. That is all you do. So that's very, very powerful. And I didn't know that I explained it anywhere, but it's in the book if you look at it. Similarly, why is E2 cross E3 equal to E231 EI? I have explained it here. It is also explained on page 32 in chapter 1, that is on vector analysis. These two formulas are there. If you go there, you will see these two formulas. But despite that, let us go through this one together in class, since I've written it out. If you have A cross B, I hope everybody knows that is EIJK, AIBJEK, where EIJK is the Levi-Civita symbol, and then this one is simply the vector ek. So this is what the cross product comes to. Now, what happens to the above when A is E2 and B is, when A is E2, remember that the components of E2 is 0, 1, 0. It's not the number of times you eat in a day. It's just the component of E2. And the component of E3 is 0, 0, 1. Now, so that means that A1 is 0, A2 is 1, and A3 is 0. Compactly, we can express those three equations in this form, that AI is delta 2I. Because when it is A1 is delta 2, 1, which is 0. When it is A2 is delta 2, 2, which is 1. And when it is A3 is delta 2, 3, which is 0. So you can write, instead of writing three equations, 1, 2, 3, you can write it like this. Similarly, instead of writing three equations for the B, we can say Bj is delta 3j. We can use the summation symbol very powerfully. So if we now write this expression for E2 cross E3, we can write this Eijk plus the AI is the ith component of E2, and the next thing is the jth component of E3, Ek. So we have just written this formula now in terms of E2 and E3. If we do that, remember that the I component of E2 is delta I2, and the j component of E3 is delta J3. If you do that, by the time you apply this substitution power of the deltas into this, you have E23K, Ek, which is exactly the same thing as E23I, Ei. You know, we are like in a cult. Most people, anybody who has not attended this class will not know that this is summation and this is summation and that this summation is equal to this summation. If you understand that and it is clear to you, then you have joined a cult. It's because it's only cult that speak to each other in codes. And when I tell you something, you understand, but anybody who is not part of us will not know what we are talking about. So let us just move on. So because of this, we can now talk about the deviant. We are now starting with we have already looked at breaking a tensor into components. We now want to break a tensor into the spherical and deviatoric parts of the tensor. How can we break a tensor into spherical and deviatoric parts? How can we do that? Now, if we have a tensor, first of all, let us see what is the spherical part. The spherical part, you get a real number to multiply the identity tensor you get a real number from the tensor to multiply the identity tensor. That real number is called gamma, and gamma is 1/3 the trace of S. 1/3 the trace of S. Now, what is the trace? If S is expressed in its components, S is Sij, Ei, circle, Ei diad, Ej. If you take the trace of S, you remember that you are going to change this diad to dot. If you change it to dot, it gives you delta Ij. So you have Sij, delta Ij, which gives you Sii or Sjj, choose whatever poison you like of the two of them. Doesn't matter now whether it is delta Ii or delta Jj or delta Kk. They will all, when you expand the addition, you get the same thing. So the trace of S is simply Sjj or Xkk. So if the spherical part is 1/3 the trace of S, by definition, and then you now know that 1/3 the trace of S is 1/3 Skk. And if you go back to our definition of the identity tensor, this is one way to write the identity tensor is delta Ij, Ei diad Ej. So you have this. So if you form this thing from S by taking its trace, this becomes the spherical part of S. Now, what is the deviatoric part? All you do to get the deviatoric part is to remove the spherical part from the whole tensor. If you remove the spherical part from it, what you have left is called the deviatoric part. This is very useful in stress analysis because it is known that it is not the stress tensor that leads to failure. It's the deviatoric part of the stress that leads to failure. So this is not a trivial decomposition. This is an engineering-inspired decomposition. So it came from engineering. In fact, if you use any SolidWorks or Solid Edge, you will see that this deviatoric part is always called for when they talk of von Mises stress. But if you didn't study engineering, you just think that is just one name. This is where it's coming from. But we'll talk about that later on. Now, for the spherical part, the trace, if you now try to take the trace of the spherical part, You remember that the spherical part is simply a scalar, which is 1/3 trace of S, multiplied by I. So if you are taking the trace, you take that scalar out, and you are just taking the trace of I. The trace of the identity tensor is 3. Why? Because the identity tensor has 0 everywhere and 1, 1, 1 on the diagonal. If you add the things on the diagonal, you get 3. So these three we multiply these 3. So when you have a tensor and you have broken it into 2 parts, you've broken it into the spherical part and the deviatoric part, what you get at the end of the day, the trace of that spherical part is the same thing as the trace of the tensor itself. Then what happens to the deviatoric part? What is its trace? The trace of the deviatoric part is 0. And we have showed it here, because the deviatoric part is just S minus the spherical part. If you take the trace, you see that it is the trace of S, but the trace of S is 0. So this page explains to you why the spherical part, if you break a tensor into its spherical part and its deviatoric part, the spherical part has the same trace as the original tensor, and the deviatoric part has a trace of 0. So we can say that the deviatoric part is a traceless tensor because it has a 0 trace. The trace of the deviatoric part of a tensor is said to be traceless. It's 0, therefore the deviatoric part is traceless. We are going to another one, which is skew and symmetric parts. We have looked at the fact that we can break a tensor into its components, 9 dyads. We can get its weighted addition of 9 dyads, which we call the components, which is akin to breaking your vector into 3 components. We also say we can break into 2. One is called the spherical part, the other one is called the deviatoric part. There is another way we can break it into 2. We can have the skew and the symmetric parts. We can also decompose a tensor S into symmetrical and antisymmetrical parts. The antisymmetrical tensor, called the skew tensor, is defined as that which is the negative of its transpose. A tensor that is skew, if you try to take its transpose, it is negative of it. So how do you get the symmetrical part? If I have a tensor S and I want the symmetrical part, what I do is that I take the tensor and I add its transpose and take the average of the 2 of them. So if you have S, add S and ST and take because if you break them into components, S is Sij Ei circle times Ej, and ST is Ji Ei circle times Ej. So that is it. For the skew part, again, what you do is you take the tensor, you subtract its transpose from it. When you subtract its transpose from it, you get the result you get is called the skew part of S. So you can see, if you look at these 2 equations, I'm sure it is not too hard for you to see that if you add these 2 together, you are going to get half S plus half S, which is equal to S. So if you add the symmetric part with the skew part, you are going to get the original thing. Then you wonder, why are you doing it? Oh, it is easier to work with the symmetrical and skew tensors than to work with the original tensor. It is easier to work with the spherical and deviatoric part than to work with the original tensor. It is easier to work with the components, the 9 dyad components, than to work with the original tensor. So the transposes, if this page explains that the transposes of if the symmetrical part is self-transpose, whereas the skew part is the opposite of its transpose. And there are explanations on this page, which I do not want to detain us because it should be easy for you to read. If you have difficulty with this page, put it in the chat. When I look at the chat, I will be putting my eyes on the chat. I can still explain it. There are bigger issues. There are bigger fishes to fry in front. So that's why I'm not wasting time on this, because this is relatively easy. So if you want to, in the component method, you can also write it this way. The symmetrical part in component form is what you have here, and the skew part in component form is what you have here. So you can see that the transpose of the symmetric part and the transpose is equal to the transpose of this is equal to the transpose of the symmetric part is the same as its transpose. This transpose of the symmetric part is the same as the symmetric part. So the symmetric part is symmetrical. That's why we call it symmetrical part, because a tensor is symmetrical when the tensor and its transpose are the same. A tensor is skew when the transpose is negative, and you can see here that the skew part is negative of its transpose. It is often more instructive to prove this in direct form whenever possible, and that's what we did here. We proved it in, this is the direct proof without breaking them into components, and this is a proof by breaking them into components. If you ask me, I think the proof without breaking them into components is neater and nicer. So symmetry of deviatoric parts. No judgment can be made about the symmetry or skewness of a deviatoric tensor. However, its symmetry is wholly dependent on the original tensor from which the deviatoric part is taken. If the original tensor is symmetric, the deviatoric part will be symmetric. If it is skewed, this deviatoric part will be skewed. But there's no question about the spherical tensor. Every spherical tensor is, by its definition, a symmetric tensor, because a spherical tensor has nothing on its off diagonal. So it's self transpose. So in what we have seen now, we have seen that if you break a tensor into symmetric and skew symmetric, the symmetric part is symmetric, the other one is not symmetric. If you break it into deviatoric and spherical, the spherical part is symmetric, but you cannot say anything about the deviatoric part. What it is going to depend on the original tensor. If the original tensor was symmetric to start with, then that there will be no problem with that. So let us go on. So this is the real issue, and it is from here I feel sad that I don't have a lot of time to really deal with this. This is the real most important thing to continuum mechanics. By the time we finish this, we will be doing calculus of tensor, and you'll get excited because you are seeing calculus again. But the algebra of tensor, which we are dealing with here, is far more important than this calculus, because it's what tells you what we are going to do with the tensors. The calculus is telling you how we are going to do it, but the what is in the algebra. The how is in the calculus. In continuum mechanics, for instance, we are concerned with changes in shape of objects that have been subject to mechanical, thermal, and inertial loads. So we want to look at changes in shape. Now, we shall see later that this creates important important tensors such as stress and strain and deformation tensors. We're interested in what happens to line material elements where such strain and deformation have been created by external loads. Let me explain to you what I mean. Imagine you have a big sheet of steel, and that big sheet of steel has been heated in a furnace. You agree with me to expand. Let us say you have an infinitesimal line element, which we call a vector, that you etched into a particular part. You want to know what happens as a result of the heat you have put, you know it will expand. So that vector line element in a very small area, let us say you are using a microscope to look at it. It is so small that it still remains straight. You know that even curves, if you look deeply, you can always make a curve out of line segments. It may be very, very, very small. So that we can say that vector has been transformed as a result of the heating. The tensor that is responsible for that is called the deformation gradient. Don't worry, just know that there is a tensor that is responsible for the changes in all those line elements. So if you had an old line element and you want to get the new line element as a result of the strain, all you need to do is to take the deformation gradient tensor and apply it to when you apply it to any line element, you will get what the result will be in the deformed state. That is called the deformation gradient. We know that. That is actually the basis of continuum. That's one of the fundamental bases of continuum mechanics. You want to calculate the deformation gradient. It doesn't matter what caused the deformation. It doesn't matter whether it is caused by heat. It doesn't matter whether it's caused by stress. It doesn't matter whether it's caused by a combination of all of this. Every line element there has been transformed by a tensor. Now, we have a very important question. And that important question is going to be answered by a mathematical construct that if I do not explain to you what it is doing, you will just think you are doing terrible mathematics. Like somebody was so disappointed last week when he was asking me, what are we doing all this theory for? I will dwell on that and I will give you a lecture outside the range next week because I want to show you where these things really go because they are not too far from you. You are in the modern world and many of you are IT conscious. You should know now that it is not it's not by welding you make an aeroplane. There are fluid mechanics, aerodynamics, and so many theories that go into it. And the manufacturing processes these days are more a matter of computing, a matter of computer software analysis. It is these things that are programmed into the computer that make that possible. So I will tell you more about that when we have the time. So, what simulation? Why so much theory of tensors? So much theory of tensor because all the equations are written in tensor form. So if you don't understand tensor, you cannot even understand the equation and you are a non-starter. I wanted to show you this. This is what I'm teaching at the 200 level. I'm showing them how to make things. And tomorrow we are going to be making this. We are going to be making this fan tomorrow. And then when we make the fan, we make the blade. We make the blade by doing some graphical analysis and stretching and lofting. There are so many things we do to make the frame. So when we make the frame and when we make the fan and the thing moves like this, the question is this: how does an engineer decide? How does an engineer decide how many blades he should have? How does an engineer decide how the blade should be shaped? How do we do that? We do that by going to the theory of fluid mechanics. We are going to put this in a simulator and we are going to put the air to it. What is the simulator doing? The simulator is using the tensor equations of the motion and it's now calculating for you and the optimal. It will tell you, okay, how much air is being pulled without going to any lab. You can know just by applying the equations using finite element analysis to your Fusion 360 and you can get it. Because of all this deviatory tensor, it is those things that are programmed into the computer. If you do not understand how to use them, you will stay at craftsman level forever. That's not a curse. You can be rich. You can still buy your Tokumbo Mercedes-Benz or brand new one. Doesn't matter. But you will remain at that point permanently. So you can see that the theory is not for joke. That is what moves your drawing to design level. It's only when you simulate your drawing and you now are able to decide from theory what parts to include that you are now doing design. So that is what I don't want to go beyond that. This is what I'm teaching at 200 level. I'm teaching it tomorrow. So let us just go on. It will be our business to demonstrate. That is in chapter 4. Unfortunately, you are not going to get there while I'm with you. That small line elements are transformed by applying the deformation gradient tensor to the original vectors of undeformed line elements. We can prove it. We can demonstrate it. Now, the question we are trying to answer here is, if I know how to transform the line element, the vectors, if I know how to transform the vectors, what does it say about the transformation of the areas? What does it say about the transformation of the volume? Suppose I have a particular infinitesimal area in the undeformed body. How can I calculate the area in the deformed body without measurement, just based on the information I have about the deformation tensor? That's the question. The third question is, if I have a parallelepiped, which is a small volume in the original thing, if I know how the lines, the vectors that made up the parallelepiped have been transformed, can I get how the volume will be transformed? We will show that when a tensor transforms lines, the corresponding vector areas are transformed by the cofactor of that tensor. The corresponding volumes of the parallelepiped for these three vectors will be transformed by the determinant of the tensor. If you look, you will see that what we are talking about now, the cofactor, the trace of the cofactor is the second principal invariant, and the determinant is the third principal invariant. Those invariants we are dealing with are not trivial matters. They are coming from engineering. They are not coming from math. And by the time you get to chapter 4 and you are looking at kinematics, you will see that that is actually what you use to design. Okay, so let us move on. So look at it this way. I want to introduce the cofactor this way. This is the original shape undeformed. And we are saying that this is, we are using straight lines because we are zooming, we have made it very, 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 very small, that the straight line is still straight. It's so small that the straight line is still straight. We are magnifying it. So you have a vector u here, and you have a vector v. If, as a result of the transformation, u transform to tu, you know, tu is still a vector, but it's a different vector from u, because the tensor of deformation has transformed u to tu. The same tensor of deformation has transformed v to tv. So the parallelogram is now like this. This was the original parallelogram. The question is, what is the area of this transformation? Oh, if you can calculate tu and tv, if you can calculate them, of course, it is tu cross tv. But suppose you don't want to calculate t. What do you need to calculate to be able to get it? If all you know is the area of the original, no problem. Just get me the cofactor of the tensors. And so where the lengths are transformed by the deformation tensor, the areas have been transformed by its cofactor. The cofactor is critically important. It is important because when the tensor has been transformed by its when the line vectors have been transformed by the deformation tensor, the areas have been transformed by the cofactor. What that means is that when you are here, you can go from this to this without knowing t. If you, all you need to do is calculate the cofactor. Once you calculate its cofactor, apply it to this area. When the lengths are being transformed by a tensor, the areas are being transformed by its cofactor. So the tu cross tv, which is the area of this parallelogram, is the same thing as operating this, not with t now, but with t cofactor, the cofactor of t. That is the definition of cofactor. Every other definition you see, whether it is in a math book or in an engineering book, we can derive that definition from here. This is the physical, important, practical definition of the cofactor. And this is what makes the cofactor important enough for us to study. So, vectors u and v have both been transformed by the same tensor t to tv and tu. How is the vector area tu cross tv created by these two vectors in the transformed state related to the original vector area u cross v of the parallelogram as shown? The tensor transforming the area of the parallelogram sides that have been transformed by t is called the cofactor. That is the definition of the cofactor. This is the physical meaning of cofactor. Any other definition can be obtained from this physical meaning. Now, here, there are there's a little bit of rough math. Not rough math. I will make sure that you can move from one step, every one step to the other will be clear. So it is for you to now sit down and make everything make sense. The first line here, what we are doing here is that we want to find the components of the cofactor. We are saying, suppose we express the cofactor in terms of EI and EJ. What then would TC be in terms of the things that were in the original, in terms of the coefficients of the original vector? So this is just our explanation. Just like I'm telling you to find the components of a vector f, and you say it's okay, it's equal to f1e, f1i, f2j, f3k, and then you now use that to now find what f1 is, what f2 is, what f3 is. So we introduce tijc, and that is what we are now going to find. Now, if this is tijc, this first expression, I'm sure is clear to everybody. So let me I want to go to the chat room now and be sure that everybody in the class knows what we are talking about here. So please tell me if you know, if you are happy with the first line, and then I can, before I move on. Tell me if you're happy with the first line, then I move on. Yes, I want more answers, more answers, more answers. Have you seen the first line? Is it okay? Is it clear? Only one person has responded. Please, we don't have a lot of time. Respond quickly so that we... Okay, so generally, so if anybody doesn't understand, just check with the people who understand it. So let me move on. Okay, so that's the first line. In the second line, I went to page, you remember that if EI is half EIJK EJ cross EK. This is something we derived in our vector analysis. And if you've forgotten it or you don't know where it is, go to page 32 in chapter 1 of the book. These two formulas are there. So what I have just done is to use this, is to take to use this to replace EI and formulate EJ based on it. So EJ, because I have EI, instead of JK, I use alpha beta. And then instead of, since J is here, I use N. So this expression and this expression are just replacing, this one in this place. So there's no problem. So because the two halves go out, that's why you have 1/4. You have EI alpha beta, EI alpha beta. Those are scalars. E, J, M, N, they are scalars, they can come out. But E alpha cross E beta is a vector, so you have to be careful about relocating it. And then TC and that times this. So what we have just done is that we just moved the scalars around on the second line, nothing else. On the third line, what did we do? On the third line here, what we do, sorry, on the next line, what we did is 1/4. We changed this. I want to test you now. Who can tell me why this expression in the bracket here is the same thing as this expression in the bracket here? You can tell. Please go to this chat room and type it. Why is this? I want to see how many people can see that immediately. No, that's not the definition of the cross product. Yeah, Emmanuel Adenekon can see it. Yes. Yes, you can see it. That's the definition of the cofactor. It's not the definition of cross product, it's the definition of the cofactor. Because if you use a tensor to transform two vectors, then it is the same thing as using the cross product of those two is the same thing as the cross product of the original vectors being operated on by the cofactor. That's the definition of the cofactor. So, good. So there's no problem there. And you will see that there will be no problem anywhere along the line. You will see everything will just be clear. Okay, so let me continue from the current slide. This page can make somebody dizzy, but it's because this is not what you had in the old thing. This is one of the things I did to express. So what you have here, what you have on this first line is expanding that last line. So let us just go back again and see. You see, it is coming from, if you go to question 1.15 in the book, you will see that A cross B dot C cross D is written as AC BD minus BCAD. This is something you have to work out. If you have been doing your tests, you would have faced this one. That it is that expansion we have used to obtain this. That expansion, this expansion here, that is in vector analysis. You can see why I was focusing a lot on vector analysis. If I was to depend on the vectors you claim you knew before you got here, I would have been in trouble by now. I would have been just talking to myself. So I knew that I had to build up your vector analysis before we even started. Okay, so this is, so if you, this is, just apply this to the last equation, you get this thing I have here. So once you got this, what I have done here is to open this square bracket. Open this square bracket. You can see that 1/4 EI alpha beta EJMN is multiplying this product and it's also multiplying this product. So as it is multiplying this product, you have it here. As it is multiplying this product, and there's a negative here. You'll find that by the time you get to the next line, that negative just suddenly transmogrifies into a positive. Why? All that happened is that I only did a small change. If I swap alpha and beta under this antisymmetric sign, it changes it into negative. So all I did is from here to here, where I just changed alpha and beta's location, because this is an antisymmetric thing. Once you just swap two, you just get negative. So that brings this negative here. The next line, what I did from here to here is that everywhere on this, in this equation, everywhere there is alpha, I write beta, and everywhere there is beta, I write alpha. In the entire equation, if you do that, you are just changing the roles of the W variable. Changing the roles of W variable does not alter anything. So you can see that where I have beta, it is alpha. Where I have alpha is beta. Where I have beta is alpha. Where I have alpha is beta. So I changed the roles of alpha and beta completely, and that does not change anything. But if I change alpha and beta under this one alone, it changes sign. But if I swap the roles throughout, it's just a W variable, doesn't change sign. So the reasons are now put here. These are the things that are different in this notes compared to what you had before. So if you look at this and this, you will now see that these two are exactly the same. These two are exactly the same. So instead of 1/4 now is half. And if you now look at it, you will see that this is the alpha n component of T, and this is the beta n component of T. So this is now the components of the, these are the components of the cofactor in terms of the original tensor. It may look complex, it's not. Just, there is no line, there is no place where there's no break. And if you want to write it completely in tensor form, it is now, you now put the base with it. It's just like if I tell you that the component of a vector is Fi, and I say, okay, the full vector is now Fiei. So that's what I've just done here. So you have to add this. Yeah, you can see that this is the full tensor form of the cofactor. The cofactor is too important. Don't just say, I don't understand it. You understand it. There's nothing about it than what I've said. And whatever you see in a math book or in an algebra book about cofactor, we can prove it from this point. So this is the physical definition of the cofactor. So we can, if we now want to take the invariant is the trace of the cofactor. You remember that we said if you want to take a trace, you are going to change this to dot. If you change this to dot, it's because ei dot ej. Because ei dot ej, when you open it up, you are going to get this quantity here, and this quantity is going to this quantity. You just operating your. So once you do this, the I and J become equal. We did that in the first. That one is, if you have been doing your tests, you would have made this product when two of its symbols are the same. It gives you this quantity here. And if you now apply this quantity to this, you get this trace, the square of the trace of T minus this trace of the square of T, which is exactly the same expression obtained from the definition of the second principal invariant. So the second principal invariant is the trace of the cofactor. It is the trace of the cofactor. This is the cofactor in full form. Taking its trace gives you this. That is what I was more important. That's more important to me than to waste time on the other one we saw before. So the last thing that we have here is The last thing that we have here, the cofactor for any pair of independent vectors. Let me just try and see. Two vectors that are not collinear cannot be made so by an invertible transformation. Three vectors that are not coplanar cannot be made coplanar by an invertible tensor transformation. Therefore, the cofactor TC for any pair of independent vectors satisfies this expression. So I think we can, what I was trying to do next is to show you the result you have in your textbook, that the cofactor can be related to the inverse like this. I don't really, I want you to wait through this on your own. If you have difficulty, tell me. I don't want to spend too much of my precious time on it. So that proof is clear, straightforward. If you have difficulty with it, let me know. So the last thing we are going to deal with in today's class, and let's see how many minutes I have left. 44. I have just 15 minutes in the regulation time, and we may go 10 minutes over time. So let us see. We should be able to finish. What I hope to do is to finish and give you opportunity to ask me questions, and we will clarify things that may not have been clear. In our orthogonal tensors, so we have finished. What did we finish doing? We finished, first of all, we were able to show that you can transform a tensor into its components. You can express a tensor in terms of its 9 components. That is 1, 9 components. 2, you can have spherical and deviatoric forms. 3, you can have symmetric and skew symmetric. So symmetrical and skew form. 4, we explained what is meant by the cofactor. And we showed that this cofactor, which is the same cofactor you met in your algebra, that cofactor is a very, very, very important thing to know. And but our definition here is an engineering definition which subsumes all the mathematical definitions. In fact, you can derive all those mathematical definitions from the engineering definition. It is based on physical reality. Now, in our study of tensor properties, we encounter some interesting tensors. The table here shows some of these tensors as we classify them into 2 groups as shown. We have looked at the projection tensor. We have looked at the vector cross. We have looked at the spherical tensor. We have looked at the annihilator tensor, and we have looked at the dyad. All of those ones belong to one class. Then the identity tensor, the coordinate rotation is another class. The tensors in the first group, there is something about them. They change the magnitude of the vectors they transform. They don't just transform. Once they finish the transformation, you will see that the magnitude of the vector has been changed. In the second group, it is possible for the second group to reorient the tensor, but it will never touch its magnitude. And coordinate transformation, coordinate rotation is like that. It rotates, but it doesn't change the magnitude. Identity doesn't even change anything. So these 2 classes are distinct. The second group is a member of a distinguished class of tensors. We will need to spend a little bit more time to know them better. They are in a class called orthogonal tensors. Tensors that transform quite all right, but they don't change magnitude, are called orthogonal tensors. Tensors, all the other tensors, they will transform and change magnitude. But orthogonal tensors, they do not change magnitude. Other tensors will change magnitude and will change direction. Orthogonal tensors. So if you see, can anybody tell me one tensor that I've not mentioned that does not change magnitude? I want to see whether you can remember. And I will tell you the answer. You will be ashamed of yourself when I tell you the answer. So try not to, because it is something, it's a tensor you have experienced this morning already. I will go to the chat room. There's a particular tensor that you know about, and that tensor does not change magnitude. And you have already experienced that tensor this morning. So let's go to the chat room. And you tell me what you think that tensor is. No, we've already, no, the annihilator tensor, it changes magnitude now because it makes the magnitude 0. The identity tensor, I've already known. I want outside the identity tensor. Outside the identity tensor, outside the rotation tensor, is there another tensor which you've already experienced today that does not change magnitude? Chronicle delta. The chronicle delta is the chronicle delta is actually the component of the identity tensor. So I want more answers. Identity tensor. No, you've already talked about identity tensor. I'll give you 1 more minute, and I can bet you when I tell you what this is, you will put your hand in you'll put a finger in your mouth, and you'll be so sorry for yourself that you didn't know it. It is just too easy. I'm not saying more answers. It's only the same. Okay. Oh, okay. The answers are there. Why am I? Okay, something is blocking my view. Okay. More answers are coming than I can see. Okay, I'm able to see them now. Are you ready now for me to tell you what it is? No, it's not rhetoric. Are you ready for the answer? You are ready for the answer? Yeah, okay. A plane mirror reflection. A plane mirror reflection. When you are looking at yourself in the mirror, you have been transformed by the plane mirror, which is a tensor that doesn't change. It doesn't change. It can change your location. It can change your orientation, but it never changes your size. If it's a plane mirror. And Victoria, you remember now? You remember that this morning. So you see. So it is not just the identity, the reflection. The plane reflection is a tensor. And you will see we will write, just like we're able to write the sun as a tensor, we're able to write it in a formula form. You will see the formula for the plane reflector. The plane reflector, do you agree with me that is something that changes? It changes, it can change the location, it can change the direction, but it does not touch the size. Okay, so you can see that there are things like that. Okay, so let us go back to our slides. Slideshow from current slide. Okay, so orthogonal tensors, the three we have talked about now: identity, coordinate rotation, and plane reflection. If it is reflection in concave or convex, that one changes, it distorts even. So that's a different thing entirely. So given a pair of orthogonal tensors, given a pair of vectors, A and B, a tensor Q is said to be orthogonal if QA dot QB gives you the same thing as A dot B. QA dot QB gives you the same result as A dot B. Specifically, if we allow A to be equal to B, that is QA dot QA gives you A dot A. You remember that A dot A is the square of the magnitude of A. QA dot QA is the square of the magnitude of QA. As we can see, one important attribute of the orthogonal tensor is that magnitude of the input as well as magnitude of the result will remain the same. It is a magnitude preserving transformation. Please note very, very seriously, we did not say that A is equal to QA. We didn't say that. We didn't say that A is equal to QA. In fact, QA may be in a completely different direction than A. For instance, if Q was the rotation, you can see that the rotation is not the same vector as the original vector because it is now pointing in a different direction. But if you take the magnitude of what you got at the end, that magnitude and the magnitude of what you started with are the same. So definition, what's an orthogonal tensor? Now, let Q be equal to QA. Now, what is QA.QB? QA.QB. Now, Q becomes BQA.BQB is same thing as Q.BQB, which is equal to A.B. Why is it A.B? So let us see. QA.QB, if Q is QA, so this one is correct. And why is this second expression correct? So I think, let me see. I think there's something wrong there. So we are allowing Q to be QA and B, and let's see. I'm just trying to, from the current slide. Given the pair of vectors A and B. Okay, QA.QB is equal to A.B. Now, so Q.QB is equal to A.B is equal to B.A. Recall that the definition of, you called that from the definition of a transpose. If Q.QB is equal to B, if this is true, this is true. Because if QT is the transpose of this, then instead of QT, instead of Q, we can go and write QA, because we have said QA is equal to Q. So we can write this as QA, which is equal to B.A. So if QA.QB is equal to A.B, then A.B is equal to B.A. So clearly from this, we can see that if this is true, then it means that QTQ is equal to I. A condition necessary and sufficient for a tensor Q to be orthogonal is that Q be invertible and that its inverse is equal to its transpose. So what we are saying is that if you have a tensor that is invertible and its inverse is simply its transpose, then that tensor is already orthogonal, because and it is coming from this derived expression, because QTQ is I. So if QTQ is I, then that means that because it is Q inverse Q, that should be I. So this is playing the role of Q inverse. So whenever a tensor is in this form, that means that its inverse is the same thing as its transpose. Every orthogonal tensor possesses an inverse. So that is something about orthogonal tensors. They all possess inverse. And how do you get the inverse? Just transpose it. That's the inverse. The inverse is simply its transpose. The determinant of an orthogonal tensor. Upon noting that the determinant of a product is the product of determinant, and that transposition does not alter a determinant, it is easy to show that the determinant of an orthogonal tensor must either be +1 or -1, because determinant of the square of it is 1. Some people may conclude that therefore its determinant is 1, but -1 will also satisfy this equation. So the determinant of an orthogonal tensor is either +1 or -1. When the determinant of orthogonal tensor is strictly positive, is said to be proper orthogonal. In particular, a rotation is a proper orthogonal tensor, while a reflection is not. So let us digest that. If the determinant of a tensor is +1, if the determinant of a tensor is +1, it's an orthogonal tensor. If the determinant is -1, it's also an orthogonal tensor. But when the determinant is +1, we call that proper orthogonal. When it is not 1, we say that is not proper orthogonal. So, example, a rotation is a proper orthogonal. A reflection is not a proper orthogonal. When you do that, when we see the equations of a reflection, you will see that in its own case, the determinant is -1. I think that's okay. Still, let me see how much more do we have. Okay, we still have some more pages. Okay, proper orthogonal tensors are also self-cofactor. If you are looking for the cofactor of an orthogonal tensor, it is itself. So for any pair of vectors U and V, we can show that Q into U cross V is stated as QU, cross QV. This question is the same as showing that the cofactor of Q is Q itself. That is QC of this. So this equation applies to every tensor Q, whether orthogonal or not. You remember, this is how we define the cofactor. Whereas cofactor is this. This is what you get from your algebra books. Determinant of Q to minus 1 transpose. Now, since Q is a rotation, determinant of Q, so the proper orthogonal tensor. So where is a proper orthogonal tensor, the determinant of Q is 1. So since the determinant of Q is 1, and then so this is 1, and the transpose of it is its inverse. So that means that the cofactor of a proper orthogonal tensor is the same as itself. You can see why transformation can be very useful. Because if you have transformed and you know that a tensor is orthogonal, many of the things you are trying to calculate will no longer need calculation. Because, for instance, its cofactor is itself, its inverse is its transpose. It's easier to work with. One eigenvalue of the proper orthogonal tensor is +1. And we will spend time on eigenvalues next week. And I think I want to stop this here so that by next week we are going to be discussing the other matters. But let me just go back to the chat room now. It's 12 noon, so the 10 minutes I'm looking for from you, I will use at least 3 or 4 minutes of it to answer any questions that arise in the chat room. So can you go to the chat room? If there are questions that have arisen from this lecture, let me have them. Flourish. The reason why it is called proper orthogonal is that its determinant is 1. When the determinant is 1, then it is proper orthogonal. When the determinant is not 1, then it is not proper orthogonal. Eboluwa, I saw your thing. Let me just see the other questions before I go back to the slides. Is A cross B EIJK AIBJ EIJK? This is AIBJEK. So EIJK. Or EIJK AJBKEI. Manuel Udusanya. Those two expressions are exactly the same. Write them out. You will discover they are the same. Emmanuel, those two expressions, write them out. They are exactly the same. The determinant for a reflection is -1. You will see it. We will get to it. The determinant for a reflection tensor is -1. Flourish. I hope you had that. That's why it's not proper orthogonal. A reflection is orthogonal, but not proper orthogonal. It is orthogonal because it doesn't change magnitude. It doesn't change magnitude, but the determinant is -1. That is why it is not proper orthogonal. It would have been, it is orthogonal, but not proper orthogonal. It is still something that is not proper orthogonal. It is still orthogonal. It's just that it's not properly so. It is very important for us. The distinction is very important. The distinction between, so when you say something is orthogonal, good. But is it proper orthogonal or not? It's not a trivial question, because the way proper orthogonal tensors behave is different from the way tensors that are not proper orthogonal behave. So you are not usually satisfied that a tensor is orthogonal. You need to know whether it is proper orthogonal or not proper orthogonal. For instance, the transformation of a proper orthogonal is not physically realizable, or of an improper orthogonal is not physically realizable. You cannot transform, you can transform a physical object rotationally. You cannot turn an object into its reflection physically. You cannot manipulate it physically and it becomes its reflection. If I take you and try to turn you to your reflection, I must kill you first, because I must change your left hand to your right hand, and I must change your left eye to your right eye. But I can rotate in rotation. Rotating you is a very easy thing. So the proper orthogonal and improper orthogonal have physical consequences. One of it is that an improper orthogonal transformation cannot be realizable physically, whereas a proper orthogonal transformation can be realizable. So that is the reason why we do not just say something is orthogonal just because it doesn't change magnitude. You know that the transformation you see in your mirror when you are dressing up in the morning is virtual. It's not real. There's nobody. If somebody goes behind that mirror, you're not going to find anything. It's your senses. It's just a titillation of your senses. It's not something physical. We can't find that person behind your glass. But if I rotate you, you will be rotated. You are physically in that place. So if I'm going to send a drone to shoot you, better think that my computation for the drone is made with an improper orthogonal tensor. So it is going to shoot at your image, and you are going to be safe. So you can see it can be a matter of life or death. So proper orthogonal transformations are realizable. Improper orthogonal transformations are not realizable. Okay, I have to go somewhere now. I will take a look at, I will send a redo of that page, that slide 55, if it requires more explanation, but I cannot talk more now. So have a nice day.